Now, it is our honor to introduce the first lecturer of the Taiwan Bridges Program. Professor Sir Andre Geim was awarded the Nobel Prize in Physics in 2010 and will later be sharing his experience with us. But first, please join me in welcoming the host for today, Professor Chen Wenzhang, President of National Taiwan University, to give us an introduction about our speaker.
Guests and our faculty and the students, good morning again. Many thanks for joining us on the launching ceremony of Taiwan Bridge Program. Now it's my great pleasure to introduce our keynote speakers today, Sir Andre Geim. As you know, he won the Nobel Prize in Physics in 2010. Let me give you a very brief introduction on Sir Geim. He is a rigorous professor of physics at the University of Manchester and also a fellow of Royal Society and one of the founding scientists of National Graphene Institute. In United Kingdom, he is best known of his groundbreaking discovery of a single-layer carbon atom, graphene. And graphene with extraordinary strength, conductivity, flexibility, and best known as described as a wonder material of the 21st century. So you can see the title of the speech today is Wonder Materials. And because of the discovery of graphenes, they opened the new insight on the two-dimensional materials. And it not only attracts a very extensive fundamental research, also they have many practical applications in nanoelectronics, energy storage, biomedical device, and sensors. With this very influential and groundbreaking discovery, he and Professor Konstantin Novoselov was awarded the 2010 Nobel Prize in Physics. Sir Geim not only is known about his scientific achievement, but also his creativity and playful in science. Some of us may know his experiment on levitating frog, which won the IG Nobel Prize in Physics too. Actually, he is the only one in history to win both Nobel Prize in Physics and also IG Nobel Prize in Physics. IG means 搞笑诺贝尔奖啊。So it's incredible to have that. And also, he understands the education as a core is to inspire the young generation or inspire the young mind. So when I spoke with Dr. Morowitz about, we need a Nobel laureate, he likes to communicate with our young generation. He suggests, Sir Geim is a wonderful one. So he graciously agrees he will deliver a keynote speech in 2025 Taipei International Youth Science Forum, held tomorrow in Taipei's first girls' high school. That's incredible. And also, because we NTU want to our students to understand the material and the discovery and the contribution of Nobel laureates better. So we opened a new course. We call it a Dialogue with Nobel laureates. Okay, it's a course in NTU. We hope our students can understand them the material and the contribution from Nobel laureate Therefore, they can have a broad international views and understand how this kind of contribution discovery to reshape the world. That's what the course one. Anyway, finally, I would like to thank our co-chairman, President James Liao, and hosted this event. And also, I hope we will learn a lot from today's lectures. So, ladies and gentlemen, please join me to a very warm welcome to Sir Andre Geim to deliver this speech. Thank you.
Hello everyone, do you hear me well? Yeah. Right, it's a pleasure to be here, and I'm impressed that President of your country has found time to open this series. It tells something about inspiration of the nation, and I'm not surprised that Taiwan semiconductor manufacturing is in this country. It's probably the hardest technology that humanity ever developed, much harder than nuclear or space technology, semiconductor technology these days, very intricate. Something happened over the last 20 years in material science, in condensed matter physics, in physics in general, and this is a new kind of materials which appeared, and I'm trying to give you a crash course in the next 35-40 minutes about what you probably need to be aware of, or at least it would be educational to know about. Let me start with noticing that all materials, all objects around us have height, length, and width. You won't find anything in our three-dimensional world which would have one of those parameters missing. So that's three-dimensional. Two-dimensional materials are not allowed by laws of physics, which is absolutely forbid the growth of those materials, and everything in first place comes from growing material. Growth means temperature, temperature means vibration, vibrations means low dimensional order is forbidden. You just cannot grow materials which would be strings of atoms or plane of atoms. Forbidden in nature doesn't actually mean that we can't do something artificially. And one can think about this kind of Gedanken experiment. We all know that three-dimensional materials have rows of atoms and planes of atoms, and you can think, what if I pull one atomic plane out of this material? This is actually not forbidden, because the material itself has to be grown at high temperature, and if we cool it sufficiently down, there is no longer the rule that you can't do that. This one atomic plane may be stable at lower temperatures than the gross temperature. So that's what we have done in practice. Of course, we didn't use tiny tweezers or anything like that, and the initial idea was to split graphite material, which is, like mica, very easy to split into the planes, to split it, make it as thin as possible. So if you take a piece of Scotch tape, sticky tape, to put it on the surface of graphite, you get something what is shown on this picture, flakes of graphite. If you look in a microscope, on those planes. They look black in transmitted light. It's metal graphite, and metals are non-transparent. So when you start seeing so thin pieces that light goes through them, you immediately think that these flakes have to be extremely small. And it was the first eureka moment for me when I saw that I can make graphite as thin as possible. That started with this kind of images of making graphite so thin that light goes through this material. So actually I want to say that graphite is a very popular material in scientific research for the last 100 years, and everyone who had, and in this audience there would be quite a few people who use atomic force microscope or scanning tunneling microscope. When you buy a piece of this equipment, you would be given a piece of graphite and maybe even Scotch tape to do exactly the same, to put it on the surface of graphite, to clean this surface, to study graphite itself, and you normally throw this Scotch tape with sticking flakes on it somewhere else. We didn't do that. We look carefully what happens on the surface because we wanted to make graphite as thin as possible. So we effectively pulled individual atomic plates of graphite, how they look like by naked eye. Despite it's only 1 carbon atom thick, you can see it by naked eye if you adjust the contrast and so on. And this is remarkable. I'll come later a little bit to this. Between and you, there are billions and trillions of molecules in air, and light goes through here, a single atom thickness makes it visible. You use all modern technology we have these days. This is transmission electron microscopy image, how it's in reality the material looks like. It's a lattice of carbon atoms. So people ask, okay, so what's so special of graphene? And then many people start listing properties of this graphene. For me, the most special thing is that this material exists in our world. Don't make a mistake. If you try to make the same trick with many materials which we know, say gold, iron, nickel, whatever you call copper, if you go below certain thickness, like say thinner than 100 or 1,000 atoms, and create this film would melt at room temperature because materials do not like to exist in their two-dimensional form. So, but it's extremely simple structure, chicken wire of carbon atoms, honeycomb, essentially. You don't seem to expect much from this material. But then over the course of several years, from 2004, we start looking at the properties of those materials and found something strange going on. It's not only the thinnest imaginable material and have huge surface area, it starts showing properties which very unusual, very different from the bulk material. Actually, the Nobel Prize was given for some light somewhere at the end about electronic properties of this material, rather than for all this collection of properties which we learned over the last 20 years and continue learning, actually, still now. But probably the most important what we learned from this experience that when you take a small part of something big, you expect this small part would show the same properties as the mother material. It turned out to be not correct. When you turn dimensionality from three-dimensional to two-dimensional, materials which are one atom or one molecule thick that become completely different to their parent in properties. And some of those properties are much more exciting than of the parent, as happened with graphite. So now I'll give you a few examples how unusual properties of this two-dimensional carbon material. And this is the first. It's a kind of a crash course of one slide, and few formulas are there just to give you an idea, not about the material, but why the committee somewhere in Stockholm decided to give this Nobel Prize, what for, at least in my perception. If you are a physicist and especially deals with metals, semiconductors, insulators, you would know what Schrödinger equation means. It's kind of billiard balls, wave functions, and so on. So the message is you describe the physics by an equation which is called Schrödinger equation and so on. That's kind of a big community of scientists is dealing with this and trying to describe properties of the materials with this kind of equation. There is another kind of discipline where cosmologists comes from. For them is another equation is more familiar. It's Dirac equation. And the reason for this is that in cosmological events, particles move very quickly, close to the speed of light. So then you transfer our low-speed world equation into this relativistic equation, and you have another set of equations. So two kind of universes. One, we're dealing as material scientists, condensed matter physicists, astrophysicists, particle physics. It's another kind of description because different speeds of the objects we are studying. So where graphene comes from? It turned out that electrons inside this honeycomb lattice of carbon, they mimic, they are not the same, but they mimic physics which is described by those ultra-relativistic equations. So that came as a big surprise, and that essentially you can study relativistic kind of physics, not study, mimic it in a simple, relatively simple desktop experiment. So what kind of experiments are those? I'll give you just one example. This is what particle physicist was considering not be possible to be done in the next 1,000 years. It has been known in theory as Klein tunneling for 70 years, how objects should behave in ultra-relativistic world. In our world, I don't need to explain you this image, what happens if you drive your car into a wall. If you live in microscopic world, but at low speed, then some of you know that in quantum world, objects can tunnel through the walls and potential barriers and so on. But if you live in microscopic world, and this microscopic world is described by laws of ultra-relativistic physics, the things becomes much more weird. So if you would live in a world which is described by how electrons behave inside graphene, then however wide or however high you make a barrier, your imaginary car would go through. And this is what we routinely see anyone who studies graphene and measures its electronic properties, Klein tunneling is a routine phenomenon. It's actually described why this material is so much conductive, why it conducts electricity thousand times better than copper, because the barriers are very hard to build in this material. Another example from how unusual physics is the following. I told you that it's visible to naked eye, and here you see an experiment from about 15 years ago where we make a membrane. At that time it was very hard to make even small pieces of the material, and what you see how light passing through a small aperture in a simple microscope, and you see that monolayer has certain contrast, bilayer absorbs a little bit more light. You can quantify this quite easily, and it's what it does. It absorbs 2.3% of light, and it happens at all wavelengths, at all light colors, essentially. So the material is gray. 2.3% for most people, for laymen, it means nothing. But if you know equations and put a simple theory, as we did ourselves together, you figure out that 2.3%, it's pi multiplied by fine structure constant. And with benefit of hindsight, it's not a surprise, because what we study coupling of light electronic wavelengths with relativistic light charges in graphene, and this kind of coupling is described by the coupling constant, also known as the fine structure constant, which is probably the most mysterious constant in the universe, 1/137. No one knows why it is so. Next time you see graphene, remember that you, with your eye, you can visualize the fine structure constant without much of equipment. Let me skip this example, what can be, and come to graphene as philosopher's stone. I do not mean anything from Harry Potter here. It's about what people were looking for centuries, is a substance which would turn rubbish into gold. And in a certain sense, we did find it. It's actually research done only a couple of years ago, together with my Chinese colleagues in Shenzhen, across the channel, not far from here. So rubbish, in our case, it's electronic waste. I don't need to explain what it is. Essentially, a lot of different metals are inside, and we would like to recycle it, but it's really hard to recycle, to extract those materials, especially because they come in a mixture. So we dissolve, essentially, literally, this electronic waste in aqua regia, in a strong acid, but it's possible to use other acids as well. Has been progress since then. And then you get this clear liquid there. And what we do, we pour this liquid through a collection of graphene flakes. It's graphene. If you make not graphene, but say 5 layers instead of 1, graphite flakes, this doesn't happen in graphene. Here is a clue. And what you see, that gold appears out of this liquid. It's extracted selectively and efficiently. All other kind of salts go through, and only gold comes from the solution as a salt and becomes a metallic gold, and you take it out quite easily, just burn it, and this is the final result. This is, again, maybe it's nice that it's a gold, but it's the idea why I'm showing you is to tell you how different the material is from its parent. Graphite is the most inert material we know. If you don't want a chemical reaction, you use some Petri dishes or whatever cuvées made from graphite. Monolayer graphene is catalytically quite active, and we do understand why. That would be quite a good story, but it's not the full story. Graphene has become a shorthand for many other materials, and already in 2005 we have shown that the material graphene has many sisters and brothers, other materials which are one atom or one molecule thick. And today we know probably a few hundred of those materials, and you can imagine if graphene brings such remarkable properties, then people are studying what interesting and useful you can extract using different kind of materials. That was graphene 2.0, but about 10-15 years later, we make another jump. It's to graphene 3.0. And this slide explains the logic behind what many people are doing these days. If you have a library, a collection of this kind of materials, so you can imagine doing something like this, to make a stack, a new three-dimensional materials out of those original two-dimensional materials, and you can consider this as playing a Lego game, but with individual atomic planes. Extremely extensive research area these days, and it's one of those 12 years ago, one of the first van der Waals heterostructures we can make, putting together different plates of the materials. Why do we do this? Let me give you an idea. This is one of the stacks, again, from 10 years ago, and this is the stack contains conductors, graphene, insulators, boron nitride, and semiconductor, molybdenum disulfide. And then you apply voltage, inject electrons inside, and lights go through, and this just the standard light emitting diode we make. The difference is that it's flexible and transparent, and using this kind of technology you can repeat essentially every kind of circuitry what microelectronic industry need by this kind of assembly. Unfortunately, it's not scaled yet. It's all done by this initial Scotch tape technique approach, which is modified but dealing with very small flakes. But I'll come later to what microelectronics industry needs. It's all about science, and my Nobel Prize was given for physics, not for industrial development, not for making gadgets and so on. But people practically mind, they're thinking, okay, what it is used for, what I can do for this? Is it just a scientific academic quirk, or can be used for something else? Usually 10 years, 15 years, 20 years, it's a very short period for material to go from academia to industry. Take aluminum, plastics, any material you take, it takes generations before you see products. Aluminum, no one thought it would be any useful material at all until airplane industry came around. So for 10 years, scientists like myself just wrote academic papers and speculated what future can hold. But then hundreds of companies around the world appeared, started making graphene. It has been produced in tons and in square kilometers. And when you have a supply, industry starts thinking how to use this material. And over the last 10 years, there are so many applications which were considered in the literature. Some of them is complete nonsense, some of them are very distant in future, but some of them has become a reality. And at home, I probably have 100 or so different gadgets and products which contain graphene. In some cases, graphene doesn't do anything but increases the price. For example, the skis are probably nothing else, just a gimmick. This watch from Richard Miller, Swiss watch, it contains graphene and it costs, well, $1 million. Okay, so graphene contributes a little bit. But other products, especially like Huawei microphone, LED cooled, where graphene is not even visible, it's on the back on those LEDs. They play a small but important work on cooling electronics, and it is probably the biggest application. High thermal conductivity of graphene is used to improve functionality of many electronic products. You probably think that graphene is irrelevant of you. It's a Nobel Prize winning material somewhere else in academia and etc. If you have an electric car, you can be considered as a proud owner of graphene-based technology, because modern batteries, lithium-ion batteries, they add to anode, but also to cathode, a bit of graphene, a few 100 grams per car, probably. It's increased your mileage by, I don't know, Cattle. It's the biggest manufacturer of iron lithium batteries, and likely you have in your cars or somewhere else, they keep it commercial secret, but it's from a few percent, maybe up to 10% improvement in the quality of electric mileage of electric cars. Another example is where graphene comes from. After a few years of trial, graphene was added to asphalt, tarmac, and the trials were so successful, it's increased the price by 20%, but durability of surface coverage was more than twice longer. It served especially in sunny climates. Another example, it's also a big application of graphene, is adding graphene to paste, to paint, makes a little bit magic. For if you cover your ship with this paint, those small creatures, barnacles, seaweeds, They do not like, somehow, no one knows why, they do not like to grow on the surface of the ship. It's non-toxic, but they still don't like it. And because they don't grow on the surface, the friction is reduced over the time. So Finnish firm Finlines covered one of the ships with this graphene paint, and over a typical period of service, 3-5 years, they found about 12-14% savings in fuel. So it's a small but valuable contribution to climate change, to reduction in energy and emissions. And now they repainted, last year, they repainted the entire fleet. But any community, including community of people who deal with two-dimensional material, they always dream big. And we have a dream for two-dimensional materials. Those applications I described, they are just small improvements which we do not notice. But what people want, and this is an advertisement by Samsung from about 10 years ago, and that explains what we want, what we are working at. I mentioned those flexible and bendable electronics, which is possible by graphene 3.0, kind of electronics, which may be in the future. How many years would it take? I don't know, but eventually these materials coming into electronics for sure. So we'll continue dreaming for the next 20 years. And the question is, the answer I don't know, are we at the dawn of two-dimensional materials? And what we know for sure is that in terms of scientific contact, there has been ongoing revolution in many research areas, not only in physics, but also as far as medicine. Graphene is used to brain implants and so on. So that's no doubt at all. In terms of societal impact, we just don't know. Would it remain some marginal material as tungsten, molybdenum, or these rare earth materials which are necessary, but we never bother whether they are in our products or not? Or maybe one day two-dimensional materials, especially with electronics, would prove themselves as important as silicon, aluminum, and plastics. The future will tell us. And with this slide, thank you very much for your attention.
Okay, good morning, colleagues and friends. My name is Prati. I'm a professor from the physics department at the National Taiwan University. And what a fantastic talk we have just heard. Professor Sir Andre Geim has just taken us from the graphite to graphene. And it's not only a journey through material science, but also a reminder that the nature may hate low dimension, but human curiosity never gives up, right? So let's move on to the dialogue and the Q&A session. And it's truly a great honor for me to moderate this joint forum that features two Nobel laureates, one in chemistry in 1986, and the other in physics in 2010. And you two are separated by 24 years in time, yet united here in space. You two actually share a lot in common, as we will see. All right. So to begin with, let's talk about the spirit behind your research. You both revolutionize our understanding of the atomic and the medical world. One through the mastering the chemical reaction, and the other through the creation of materials atom by atom. And you both mentioned that your breakthroughs were very much driven by your curiosity rather than by a planned application or proposal. So do you think today's research environment still encourage people for this kind of freedom of mind? If not quiet, what would be your advice for, say, the funding agencies, the professors and supervisors, and even for the younger generation? I know you both share a lot about this in public, so perhaps you could just highlight some of your thoughts and share some of your stories. So maybe we could start from Andre. Okay.
When I went to the United States,
Right.
the first thing which impressed me most is the relation between mentor and student. Because in America, students will always ask a lot of stupid questions for professor to answer, but professor cannot give stupid answer. So the dialogue is very interesting. And part of the different dialogue is because of the democratic training. The young people, when they grew up, they were respected. So they have to ask questions, ask stupid questions. As Lana Sporin already said, that the student ask a question, professors, and professors turn out to be wrong. That's the moment science makes progress. Otherwise, student will be only a good student all the time.
Right.
So that democratic education in the United States have influenced the science education.
So how would you compare like 20 years ago and now, or like 30 years ago and now? You think there is a big change in between?
10 years ago, I already became old. So I could not answer that 10 years ago what's the difference between Taiwan and 10 years. Then 10 years ago, students already dare to ask a lot of questions.
Right.
No, it was 30 years ago there was a difference.
I see.
Students didn't dare to ask questions.
Okay. Right. So Guy?
I always try to fight with agencies for blue sky research, for curiosity-driven research, because it's eternal fight, one piece of fleeting dream at night. Some poets said this, because there is always pressure of politics, of people who do not understand how science is done, to say what it is good for. You are doing too academic research, where is scientific impact? And they completely forget about that our technology, modern technology at certain moment was just driven by human curiosity. We all know that, and I think the pressure has been always there. I would say pressure, it increases, you more and more paperwork you have to fill in to prove how your research would be important for future generation well-being. Sometimes it's impossible, and we all play this game. We all know that, but what we don't know, let me tell you a story which I like to tell, especially people from funding agencies. Once I was on a boat trip watching dolphins, and it was quite an unusual trip, because dolphins suddenly start going close to the boat and talking to us, just seems to be you can reach by hands them, and they wanted to communicate with humans. You can imagine, I have never seen anything like that before. Also, I swam with dolphins and have several occasions seen them. Somehow they decided to send us a message, and you can imagine it's magic moment, kind of everything is at awe. About 7-10 people on the board of this ship. We're all just holding our breath, what's going on. And then a little boy behind shouts, "Man, can we eat them?"
The dolphins?
You see, spoils everything. So this is the pressure we have seen. Sometimes you find curiosity, you find something you don't know whether it would be good or not. Right. And each time this calls, "Can we eat your research?" Fortunately, we can prove that with graphene we can eat it, but it was not obvious, 20 years ago.
Right. Because you also mentioned several times about the funding agencies like the European Commission. And do you think you are being successful, or say you have succeeded in kind of trying to change the environmental culture, in this regard to encourage longer-term research rather than the short-term, short-sighted projects?
I try to do my best, but it's certainly not enough. It's the pressure of taxpayers, which is more important than the pressure of some individual Nobel laureates. So it's they remember this kind of stories for 5 minutes.
You made a very
even less
in the banquet.
Even less than this one, and then it's forgets, it's politics. So what we need educate general public that curiosity is very important. Blue fundamental research, which seems to be completely useless, like making thin pieces of graphite. What it can be used for? Can you eat it? No, of course not. And general curiosity is what makes the difference between humans and cavemen.
Right.
Us, civilized and cavemen.
Okay, so next, let's move on to about reflection on the social or societal role of the scientist. You both spoke publicly about the social responsibility of the scientist, right? And in today's environment, we have seen a lot of progress, like new materials and new technologies reshaping our world very rapidly. So what kind of advice would you provide to the younger generation or different parties in balancing their innovation with ethical and environmental responsibility? For example, Yuan Li has extended your vision from the molecular scale reaction to the global scale sustainability. And Sir Geim, you talk in public a lot about your care of human society. So perhaps you could share with us about your thoughts and your stories.
Yeah. If I understand your question correctly, how can we can save the world
or it's just like
how society can save the world? Yeah. My answer wouldn't be politically correct, and I think there is a lot of wishful thinking going around. One thing is, which is probably most annoying for me, when someone comes by airplane or by electric car to a meeting which discussed an environment and how we save it. It's all gimmicks. Really, most of technologies, even such nice technologies like solar cells and so on, they are not a fundamental solution. The temperature will rise, we use more energy, it's all recycling is postponing the dead end rather than doing it. So the biggest, if you want to save the planet, I'm afraid the only solution is to have one child. And because if you're vegan, vegetarian, whatever else, you need living, you need housing, you need food, and etc. And you can't save more than 40-50%. Economists, in terms of energy, economists have done this work. Impossible to make savings. So the only possibility to reduce your environmental impact to have not 4 kids but 1. And I'm afraid it's scientific fact which politicians hide from us very, very successfully. In terms of technology, a salvation rather than solution is probably nuclear fusion. If it's done within the next 20-50 years, we have a solution, because nuclear fusion is really something free energy essentially, and we can air condition our planet, we can do a lot of things and so on. That's probably the biggest scientific, not really scientific, the biggest technological challenge we have. So one, education, and reduce the number of people on the planet, which is political, societal challenge. It will take generations, and another one is probably nuclear fusion. That's my view. And it's not, as you see, politically simple.
Right. We all know that technology comes as a two-sided sword, right? For example, like E equals mc squared produce the energy efficiency, but on the other hand, it's also caused a lot of human disaster. So when you mention the, for example, the nuclear fusion, would you have any concern about the possible associated disaster for the human society?
I said nuclear fusion. It's different from the current technology, which is nuclear fission. Fusion much more safe. It's not, there should be no like Chernobyl or Japanese disasters, though by technology should be spoiled, but
safe technology.
Much safer technologies, but you know, you can't blame technology for the disasters. It's people who are responsible. Every new technology you can use either for good or for bad. So
following that, how about the AI and even quantum computing? You know, people are talking about this all the time. I don't know if you have any thoughts on that.
AI is an interesting question. It also tells us how poorly educated we are. It sounds like a new technology, but first AI was, if I remember correctly, the first AI project was in 1965 when people started dealing with this. This is one of those cases where quantity turned into quality only, 10 years ago when people from Google, I believe, they showed how to scale up these large language models, that it has become very rapidly, within 10 years, it went what we know it now. It's a great technology as it is now. It's not intelligence, of course, it's pattern recognition, which not much different from pattern recognition when you open your computer and you don't need a passport. It's the same principle, but the scale, the number of operations dramatically increased. So it's not intelligence. General intelligence is coming. We don't know yet when, but in my opinion, there is nothing to worry.
Okay.
It's, for me, worries are humans because we live on instincts, and those instincts are not very good. Intelligence, by definition, can't do anything wrong because it's intelligence. When we think intelligently, we wouldn't have wars and all other conflicts. So, from general philosophical perspective, I don't think there is any worry. From another perspective, economics and other societal perspective, it's also no worry because a human race, it's also a very developed general intelligence. We somehow associate our society with individuals, with ourselves, and we call ourselves intelligent, and we are intelligent, but we possess something more. We possess society, and the society is multiplication of all intelligences. So, as a human race, we are much more than individuals. So, with all those databases and so on, we are very competitive with general intelligence, whatever it will be, silicon-based or something like that. And we have a big advantage. One human, in order to function properly, we need 2 bananas a day. AI needs a nuclear power station, and general AI would need many, many power stations to drive. We are very efficient in terms of processing information as individuals and as a human base. So I can't see energy resources to compete with intelligence of the human race in general. So we're safe on this side as well.
Right, we'll see how it goes in the near future. Right, so how about Yuan Li?
Well, when we talk about fusion, for a while, people did not worry about whether fusion will be successful. They worry about when fusion started, all the AI and everything will not have barrier to start to fuse, and mankind will disappear. So it's not the success of the fusion, it's the success of the fusion will eliminate everybody. And that was a worry.
So you mean the current bottleneck we are facing about energy supply is actually a good thing for the modern technology not to be overdeveloped?
Yeah. No, I don't remember, was that in this room? Stephen Chu, Energy Secretary at the time,
right.
He came and he said, not in this century. He didn't believe that fusion would be successful in this century. You have to wait a little bit longer.
So we are all still safe for our current life.
Yeah. But when we approach the end of the year, we're now approaching the end of the year now, you notice 2 things. One is there are lots of announcements of breakthrough in the fusion, especially Los Alamos National Laboratory or another national laboratory will announce that they had made some breakthrough in fusion. It means they want more money from the government. But every year they will make announcements that they had some breakthroughs.
Right.
Breakthroughs.
Yeah, in the past few decades, we all know that you've done a lot regarding the global sustainability. So maybe you would like to share, your advice, and you've been doing this really for decades. And what would you see the current status on the things you've been working on, and what kind of advice you want to offer to this great audience here? Yeah.
Well, when I entered the National Taiwan University, I had two goals in mind. One is I wanted to be a good scientist, and this is one thing I want to do.
You made it already.
And second thing is I want to work with idealistic people to make this world a better place.
You kind of done it all as well, right?
With this goal in mind, I went through for last 60-some years. I keep thinking about these two things.
Right, so it's like your core value that never changed through the past half a century.
Now, I want to work with idealistic people to make this world a better place. So when they're invited to be able to work with young people to make this world a better place, I usually say, yes, I have come.
Right,
And
right.
like today, I really didn't feel very well, but I still came.
Yeah, right. So I think Sir Geim also have been trying to do similar things for some time after you won the prize. So do you think winning the prize, the Nobel Prize, actually helped a little bit, to make your advice or words more weighted for a certain audience, or you think that they are?
When I left Taiwan in 1962, long time ago, when airplane took off, I keep on thinking, how can I leave Taiwan? Taiwan is such a horrible situation, and you just left Taiwan and went to the States. But 10 years later, when I came back, I was a tenure professor at the University of Chicago. And one thing I found out was a professor in a university have very little influence. Very little influence to the society or even to the university. So when I went back, then keep working. And then I found out when I was elected to the member of National Academy of Sciences, then people will start to listen to me. So I thought, the member of academy and things like this is not that unimportant. And so after I won the Nobel Prize, then people will listen to me. So I remember when I was attending that conference, Professor Bernstein took 10 of the students and asked my question. Before I started to talk, he told all the students, listen carefully, listen. I made me very nervous about my responsibility or things like this.
I see.
But think aside.
So sorry.
As a student and postdoc, and I did 2 postdocs. In both cases, professor said, Yuan, you can do whatever you want. And he took sabbatical and left for England. And second postdoc at Harvard University, again the same. So you do what we want to do. And he left for sabbatical. So I always said the best research advisor was the one who gave you opportunity, but leave behind you yourself, to work yourself. And that's the best case.
Right.
So I still believe in this.
Okay.
I took a student and
It's quite very encouraging. Yeah, excellent. Because we are now running out of our time, so before we close the session, would you like to offer some take-home message for the audience? Maybe Yuan Li? Any advice for the younger generation? Yeah.
The same question. What advice?
Yeah, I mean, just any,
For the younger generation,
yeah, like anything related to, for example,
I would say that in my educational processes, 1.5 years when U.S. is bombing toward the end of the Second World War, B-29 was flying very high. Japanese artillery would not reach, and they are bombing every day. The scattered tin foil, we want to collect a tin foil on the ground. But then we ask the question, is this safe? When the airplane is on top, the bomb must be dropped way ahead of time to reach you. So is that safe? So when we were kids not attending school, we asked a lot of questions about the bird, about the airplane, about the bombing, and that without attending the school, I call 野放, the blues outside and learn from the nature. That has been most educational for me. We did learn a lot from nature.
I will keep
Practical pressure.
Sometimes I saw the bird is making the nest and climb up and observe the bird building the nest and then lay the egg, bring and tie the nest down and grind the rice and feed the bird and let them grow. And we did a lot of things, which was interesting.
Right, great. All right, so I think we've run out of our time, and I'm sure the great audience here have learned as much as I do about the wisdom from the two laureates. So please join me to thank the two laureates again.
Thank you, Professor Sir Andre Geim, Dr. Lee, and Professor Wu for the wonderful discussion.